Welcome to ShapeBuilder 15. In this video, we'll walk you through the major updates in the software and show how these new capabilities deliver more accurate and realistic results. Let's get started. ShapeBuilder 15 introduces an enhanced analysis engine that can now account for material yield strength in normal stress calculations. Previously, ShapeBuilder performed only elastic analysis where stresses increase linearly with applied loads. This could overestimate the normal stresses under high loads. The new elastic plastic analysis performs a nonlinear calculation that considers each material's defined yield strength. Once a material reaches its yield point, stresses are capped at that limit, giving more realistic results for the section under load. To help visualize this behavior, ShapeBuilder 15 also introduces plate result diagrams, a new way to see stress distributions across the section. To demonstrate these new features, we have added a W36 by 135 steel beam from the database to the project using A992 grade 50 steel. This beam has a 10-inch by 1-inch top cover plate and a 14-inch by 1-inch bottom cover plate, both with A36 material. Now let's switch to the Analysis View tab and apply a strong axis bending moment of a negative 30,000 kip inches to the cross-section. In the legend, we see the maximum tensile stress is 33.5 KSI, and the maximum compressive stress is a negative 37.9 KSI. With the flyby info enabled, hovering over the top plate shows that its stress exceeds the material's yield strength of 36 KSI. That's because the analysis type is still set to elastic, which does not account for yielding. Switching the analysis type to elastic plastic causes the solver to recompute the solution, accounting for the yielding of the material. We can hover over the section again and see the top plate stress capped at 36 KSI, showing it has yielded. Hovering over the bottom plate shows that it remains below the yield stress. Now let's take a look at the plate result diagram to see what's happening internally. We can click and drag a vertical slice through the section to display the normal stress distribution. The plot shows the top plate stresses reaching the 36 KSI yield limit, while the beam's bottom plate remains below yield. Increasing the moment to a negative 35,000 kip inches, letting the analysis run, and then slicing through the cross-section shows that both the top and bottom cover plates have now yielded. The plate result diagram clearly shows the stress in each plate at 36 KSI, the yield strength of the A36 material, while the beam remains elastic. You can see the stresses in the flanges and webs are below the 50 KSI limit of A992 grade 50 steel. Next, let's increase the moment again to a negative 40,000 kip inches. The flanges of the beams have now reached their yield limit of 50 KSI as shown by the normal stress graph. However, the central portion of the web remains elastic as its stresses are still below yield. To estimate the plastic moment capacity, let's multiply the plastic section modulus Zx, which is equal to 824.52 inches cubed, by Fy of 50 KSI, which is the base material for the cross-section. This gives a value of 41,226 kip inches. Entering this value for the applied load will let the analysis run once again. Now, let's take another vertical slice through the cross-section. We see both cover plates at a positive and negative 36 KSI, and the beam is fully yielded with all of the stress along the section being at a positive or negative 50 KSI. Note, if we try to apply a load to the cross-section that exceeds the plastic moment capacity, for example, a value of negative 42,000 KSI, the program tries to run the analysis again, but returns zero stresses. This indicates that the solver cannot converge, which makes sense, as the section cannot support more load since it has yielded completely. In addition to uniaxial bending, as shown in this example so far, The elastic plastic analysis can be used to determine the normal stresses for biaxial bending, axial tension or compression, and combined axial and bending loading. Now let's back the strong axis moment down to a negative 25,000 kip inches and apply a weak axis moment of 1,000 kip inches to the cross section. Now we can take a horizontal slice through the top flange plate and see that one side of the plate has yielded while the other side is still in the elastic range. Let's take a closer look at some of the features in the plate result diagrams. Right now, the slice is taken through the center of the top flange plate at a location of 18.3 inches. We can manually adjust the location of the slice and say move it down an inch to look at the stresses through the top flange of the beam, which we see is still elastic. Also, we can enter a negative 18.3 inches to look at the horizontal slice through the bottom plate, and we can see that part of it has yielded. Also, we can flip the slice direction from global X to global Y and set the X coordinate to 0 to see the normal stress at a vertical slice through the center of the beam. Furthermore, the resolution of the graphs can be adjusted by increasing or decreasing the point count. Right-clicking the plot lets you maximize it for a detailed view. In addition to normal stress plots, you can also display St. Venant stresses, flexural stresses, the work beam function, and more, depending on the selected result type. That wraps up our look at the new major features in ShapeBuilder 15. The new elastic plastic analysis and plate result diagrams provide a more realistic and insightful view of your cross-section under load, helping you make more informed engineering decisions. Thanks for watching and have a great day.